second unit is trigonometry. Now you've done a little bit of trigonometry already. A squared plus b squared equals c squared. But in grade 10, you get introduced to the trig ideas of sine, cosine, and tangent. So some things that we already know. For labeling triangles, did you know that the hypotenuse is always the longest side of a right angle triangle? And we only use the word hypotenuse if one of the angles is 90 degrees. It's always opposite that 90 degrees. The other sides, we sometimes call adjacent sides and opposite sides. And we'll talk about how we know which is adjacent and which is opposite in a bit. Angles are labeled with capital letters, and sides are labeled with little letters. So if this is capital A, this is capital B, and this is capital C, then we would say this side length is little a, this side length is little b, and opposite is little c. And I chose A, B, and C this way because we often talk about a squared plus b squared equals c squared, where c has to be the hypotenuse. So I made sure that in my labeling here, my c was the hypotenuse as well. The Greek letter theta is often used in trigonometry. So if this is my theta here, and I'm going to do this in green, if you have color codes, we'll just do it once in our notes, but I'm going to show it to you twice on the board. So if that's the angle theta, would you agree that this is still the hypotenuse? Yes or no? Good. Okay. If this is theta, the opposite and adjacent change depending on where you say the angle theta is. If I'm talking about this angle theta, which is right now angle B, then straight across is the opposite side. And right beside, have you ever used the word adjacent in the English language? Have you heard that word before? What would it mean if I said the dog was adjacent to the rock? Beside. Beside, next to, right? So in the English language, adjacent means next to, beside. So here, this side is beside the angle. So is the hypotenuse, but the hypotenuse is always the hypotenuse. Okay? Now, I'm going to erase the green. Oh, maybe I can just backspace. And I'm going to do it again with the other angle. If I was thinking about this angle, would you agree this is still your hypotenuse? But now this is your opposite side, and this is your adjacent side. So the hypotenuse never changes, but opposite and adjacent is based on which angle you're talking about. Okay? So sometimes I actually would recommend you can label your hypotenuse because it never changes. But maybe we won't label opposite and adjacent because we might confuse ourselves if all of a sudden one question makes us think about the angle more than once, or both angles in the same question. So the opposite and adjacent, we're always going to be thinking, well, straight across, that's always my opposite. So right beside, that's always my adjacent. So our first definition is tangent. The tangent ratio of an angle is the opposite side over the adjacent side. So mathematicians have found the following, okay? The tangent ratio for the same angle will stay the same no matter how big or how small the triangle is. All right. So I'm going to start off with an example to show you that the idea doesn't change no matter how big or how small the triangle is by using a special triangle. I'm going to start, make a right angle here, and I'm going to use 45 degrees here. This is a special triangle because if angles in a triangle add up to 180 degrees, what's the other angle in this triangle? Also 45. And this is a special triangle called an isosceles triangle. Whew. How do you spell isosceles? Does that sound tricky to spell? I'm like currently, is it with an extra C in? This is what's bothering me right now in my head. You ever have one of those words where you're like, is there supposed to be an extra C there or not? Which one is it? Without the C, like this? I guess we could Google it to make sure. We could start typing into Google and find out. Does that ever happen to you where you look at a word that you usually are able to spell?
What if it autocorrects isocles?
It has an extra S, that's why I was... There, I had an extra C, I knew there was an extra letter. I spelled it wrong twice and got you to guess which one it was. It is... Whew. Why would they make a word that spells so funny, right? Isosceles. So an isosceles triangle has two angles the same and two sides the same. So for example, if this side was 3, this side would be 3. And the tan definition is the tangent ratio of an angle is the opposite side over the adjacent side. So if I wanted to write tan of 45 degrees, I could choose either one of the 45s. So let's say I'm talking about this one right here. Then would you agree this 3 is the opposite and this 3 is the adjacent, which they're the same number? I will get 3 over 3. What does that reduce to? 1. Okay? If we go to our calculator and we hit the tan button and we type in 45, and check this with your calculator because some calculators are already in degrees and some of you might have a calculator that's using a different angle measurement called radians. So we want to make sure our calculator is in degrees, so when we push enter, our calculator tells us it's 1. Perfect. Now, if I took that same triangle and I made it bigger, kept the angles the same, they're both 45 and 45, but now I made this bigger and made it 10. Would you agree this side would have to be 10 too because it's an isosceles triangle? And now, if I did tan of 45 degrees, I would get opposite of 10 over adjacent of 10. Do you see that it's 1 again? And this is the big thing in trigonometry that makes trigonometry so powerful. Mathematicians have discovered that when you make a triangle and you measure an angle, the ratio of the opposite over the adjacent never changes. So I'm going to show you another example of what that means. I'm going to pick a random angle of 20 degrees. Okay? I'm going to go to my calculator, and my calculator already has it memorized that if you do tan of 20 degrees, you're going to get 0.3639. Blah, blah, blah. Okay? So I'm gonna go back to here, I'm gonna write that down, that tan of 20 degrees, approximately 0.3639. So then I would go, and if I had measured this perfect with a protractor, I could go and I could measure this side. Okay? And if I measured this side and it happened to be 3.6 centimeters, and my measurements probably wouldn't be super exact, so I'd be like rounding, I'd be like close enough at 3.6 centimeters, and then I measure this side, it would be 10 centimeters. Because the tangent ratio says, and if I type this in, that tan of 20 degrees, according to this triangle, is 3.6 over 10, which is 0.36. Is that close to what the actual value is? Absolutely. Why would it be a little bit off? Probably I measured not super accurately, right? I just went to one decimal place when if I had a sharper measurement, maybe this was 3.63. Now I could make a bigger triangle. I make a bigger triangle. Ooh, do you want a challenge? You guys look like you could make a little bit of a challenge. Do you want an easy challenge to start with and then a harder challenge? Easy challenge to start with. I measured this at 20 degrees, and I measured this side this time to be 100 centimeters. What would be an accurate measurement to one decimal place for the other side? Okay, I'm going to ask you in a second, Sean, but I want everybody to think about this. What would be an accurate measurement for the other side to one decimal place? All right, so if you have an answer in your head, that means you're starting to get trigonometry. If you don't have an answer in your head, that means you missed something already in what trigonometry means, and we have to pay attention to see if we can understand. Sean, what did you come up with?
36.4.
36.4. So the reason he would say it's 36.4, because if you do tan of 20 degrees, it is the opposite over the adjacent. So we need a number in here, and we know from our calculator that this is the answer. So if I do 36.4, I type that into my calculator, or I just move the decimal place over twice, that would give me 0.364, which is really close to what it actually is. Then I said I'd give you a challenge. You need 90 degrees in here. Here's my challenge. I'm going to give you one more. 20 degrees. I put this in here. And to the nearest whole number, how challenging should I make it? Medium challenge or hard challenge? Here, I'll do two of them. If you want the medium challenge, this number is 18. If you want the harder challenge, this side is 9. To the nearest centimeter, what's the other side? And now you're doing crazy trigonometry without your calculator because you knew one idea. If it was a 20-degree angle, it was 90, and you knew the opposite side was 18, what possibly could be the adjacent side to the nearest whole number? And if it was 9, what could possibly be the adjacent side to the nearest whole number? You can guess and check if you want with your calculator. If you were guessing and checking with your calculator, this is what you would know. You know that tan of 20 degrees is the opposite, so let's use the 18 first, over something, which is what we don't know, but we know that the answer has to equal close to that. What whole number on the bottom would give you closest to that? Guess and check with your calculator. If you want to do the same, if you're using the guess and check method, actually 18 and 9 are equally as easy or difficult. Right? Because all you would do is you'd go to your calculator and you'd say, maybe it's 30. Does that give me 0.36? No. Well, this is like 36% on the test. The test would have had, if I only got 18 out of 30, I passed the test. Makes sense, 60%. So it's got to be a bigger number. So, well, if it was out of 100, it would be 18%, so it's got to be less. Come up with.
I think I got it.
Okay, what did we try?
I tried 50.
50. That's pretty darn close, right? If you want to see if you tried 51, does it get closer or farther away? Farther away. If you tried 52, does it get closer or farther away? Right? That's a good way of using guess and check, right? 50 is the right answer. Now, we did that with our calculator, and we see how we could use no calculator to figure this out.
Well, since for the 36 one right there,
Mhm.
100, and then 18 is half of 36.
18 is half of 36?
Half of the 100, and then
Okay.
I get it.
And then did you get the green one as well?
I didn't do that one,
Okay.
but I feel like it
Should be 25.
It should be 25. Look at that. Because it's half of 18 again. So we have this idea of a ratio of fraction. The definition of tangent is that tangent is always the opposite over adjacent. This became super helpful in figuring out all sorts of things for building way back to like thousands of years. It means that if you wanted to build something a certain height, so that a certain distance, if you went 7 meters away, and this was 20 degrees, you now could figure out what this is. Because they would know that tan of 20 degrees was that 0.36. So now I have tan of 20 degrees needs to be this question mark over 7. Let's start guessing and checking and see how close we can get to 0.36. What do you want to do over 7 to start? 36% on a test out of 7. What would be a good place to start? 3 out of 7? How close does this come to 0.36? It's a little bit too much. So you try 2 out of 7? Too low. What would you try next? 2.5 out of 7. Let's see. Ooh, that's really close. 2.55. We need 363. Oops. 2.55 divided by 7. We need 3637. Ooh, we're really close. What do you think we should do if we want 3637? 2.54 divided by 7. Too low. 2.54. We need 37. Thinking 5.4. Higher one or lower in the, what do you think? Do you think I should use a 2 or a 7?
2.
2? Okay. Try the 7. Oops. Ooh, 7's really close. Maybe. And we could keep doing this and get closer and closer. Right? But mathematics guessing and checking is decent, gets us a right answer eventually, but usually it's not very efficient, right? Can you imagine, you come to class, and instead of asking your name, I'm just going to guess until I guess it right. It could take a while, right? Might be a little bit quicker if I guessed all at the same time, right? So if I said a name, and I said Frank, nobody puts up their hand. But then if I did guess Sean, I'd get 2 and 1, it'd be like, this would be good, and Sam would work out well that way too. But it would take I probably could get most of your names eventually. And then some names you could probably guess for a very, very, very long time and not get them. That wouldn't be a very good strategy. A more efficient strategy would be like, what's your name? And then you would tell me. And then that would be easier. Right? Or I could have the list and I could just say the first name and someone's gonna put up their hand and I'd be like, okay. Yes.
Can I get water?
You wait until break. And I don't mind if you need water, but make sure you bring a water bottle. Okay? Okay. This is the idea of tangent. Now, what's super powerful is mathematicians before have figured all of this out. People have measured and done mathematics to figure out. So every single angle that exists, you can type into your calculator. So if I want to draw a triangle on the board accurate with 30 degrees, I go here and I type in tan of 30. Then I can go to my, right, I can draw 30 degrees and say, if I want to be accurate, according to this, tan of 30 is 0.577. Wow. Tan of 30 degrees is 0.577. If I go to my thousandth decimal place, this means that this is a fraction of 577 over 1,000. If I only went to my tens decimal place, rounded would be 58 over 100. If I only went to my tens decimal place, rounded, that would be 0.6, I would get 6 out of 10. So if I wanted to draw this accurately, I could choose 577 out of 1,000. Or I could do 5.77 over 10. Any of those measurements. And if we actually took a ruler and drew a right angle and measured exactly 5.77 and then 10. And then we took out a protractor and said, I'm going to measure that angle. We get right on 30 degrees. It's crazy. Okay? And then you could do a squared plus b squared equals c squared. Okay? If I do a squared plus b squared equals c squared here, I will get roughly, and I'm cheating, but you don't know how I'm cheating, so I'm not going to tell you. I think it'll be close to this though. But I'm not telling you how I figured that out. But you can check. If you do 1,000 squared plus 577 squared and then square root it, see if I'm close to right at 1,154. And then I'll tell you I used a trigonometry trick to figure it out that we'll eventually all learn. I'll teach it to you today maybe or tomorrow. Not tomorrow. No math. Okay. Some more definitions. We have, when we're looking straight out and we look up, so maybe we can even add an arrow head this way. You're looking out, straight out, and you look up, we call that an angle of inclination. Sometimes you'll see it in textbooks also as an angle of elevation. And if we're looking straight out and looking down, you can add an arrowhead to show that you're looking down from the horizontal line. That is an angle of depression. Anybody check, was I close with 1154? Yeah. Do you have this one next? Yep. So textbook has this in there, this interesting connection that if you want to be ultra, energy efficient and want to install solar panels on your roof, they have found that they work the best if the angle of inclination of the roof or the angle of inclination that you put your solar panel on is approximately equal to the latitude of the house. So you'd have to look on the world map, where are we latitude-wise? And if you're at a latitude of 50 degrees, you would want to have your solar panel with an angle of inclination of 50 degrees. Just kind of cool. And it kind of makes sense, right? Because depending on where you are, the higher up that you are, the sun doesn't get as high. So you would need your solar panel more straight on, because you want those sun rays to sort of come straight in to your solar panel. Right? It's not a very good idea, for example, to put solar panels in your basement, because the sun doesn't hit it. Or to have it on the north side of your house. It would still probably get some power somehow, but not very much. So having those rays directly in there and trying to design it, and have the picture here, this angle of inclination, they make that exactly the same as the sun's rays. It can be very useful, right? You could also install them, right, something like this, but then you're gonna get like leaves stuck in here and probably problems with other things. So something to consider that way. Okay, anyway, that's just interesting. Next, we're going to determine the tangent ratio to the nearest hundred. And we did this one already. So this one we can really just, it was 0.3637, so to the nearest hundred, it would be 0.36. And then, since that's 100, we can change that into a fraction as 36 over 100. Since tangent, and we'll write it, we're going to start writing opposite as OPP. Are you okay with that? Standing for opposite. And ADJ, short for adjacent. Eventually, we might just use O and A. Some people remember the word TOA, because tan is opposite over adjacent. You might have even had an older sibling ask you, are you doing trigonometry? Have you done SOHCAHTOA yet? And you're like, what? Because it sounds like a word you've never heard of. It is, because it is probably a word you've never heard of. Well, this is the TOA part of that word. Tan is the opposite over adjacent. So when you go to draw this triangle, you draw a right angle. Somewhere you need to put 20 degrees, right? So I could put the 20 degrees here because it looks like that's the smaller one. And then my opposite side would be 36. My adjacent side would be 100. But somebody else says, oh, don't we always have to reduce fractions? And they reduce this to 9 over 25. And somebody else could draw their right angle triangle, right? Does that bother you if I put it on an angle like that? It's like a little weird, eh? Is this still a right angle triangle if you twist it? Yes. Which would be the opposite side now? Well, the 20 is here, so this would be the opposite side. Maybe I put the 9 here, this is my adjacent side, and the 25 there. We can draw triangles any way we like. Somehow we're used to having it nice and flat, aren't we? With a 90-degree going straight up and down. That's how I'm used to drawing them. "35 degrees we'll do together, and then I'll leave 45 and 65 for you. So tan of 35 degrees. We go to our calculator and we find out what was the ratio. 0.70. Which would be 70 out of 100 or 7 out of 10. Draw a triangle with a right angle. I did it flat again. Pick of the two. Hey, of these two, the way I've drawn it, which one should be the 35 if I was trying to be somewhat accurate? The top angle or the bottom angle? One of them, if I make one of them 35, the other one has to be 55, so that the angles add up to 180. Does it matter which one's 35, which one's 55? Well, does one look bigger than the other? Would you agree this one looks a little smaller? Okay. I will tell you that the smallest angle always goes across opposite the smallest side. Makes sense because the smaller the angle, the smaller the side is going to be opposite. The bigger the angle, the bigger the side. 90 is always the biggest angle. Hypotenuse is always the biggest side. So this is my 35, and that would make this 7 and this 10. So use your calculator for 45 and 65, the next two on this page. And draw a triangle that goes with each of them. Okay, so your calculator's in radians. To change that, push the mode button, and then go down and highlight degree, and push enter. And now try it again. Perfect. So you can check how you did. If I take 214 and divide it by 2, I would get 107 over 50. So that would be another possibility that I could have 107 here and 50 there. Or any fraction that gets close to that number will be that triangle. So it doesn't matter how big or how small the triangle is, the ratio will always stay the same. And this is the power of trigonometry. So when a question asks you to find tan of an angle, you have to remember that tan of any angle is always the opposite side over the adjacent. So if I'm talking about angle D, it's going to be a fraction of the opposite side over the adjacent. Okay? Opposite side over adjacent. For D, the opposite side is 3. The adjacent side is 4. Again, I can label that this is the hypotenuse, but I will not label opposite and adjacent on my triangle because it changes. Because this question also asks us to find tan of F. And if I look at F, now the opposite side is 4. The adjacent side is 3. Let's change these to decimals in our head as best as possible. Do you know how to change 3/4 to a decimal?
0.75.
0.75. How did you do that?
It's just, I kind of just have it memorized.
You just have it memorized. Do you have any ways that you remember
3/4.
3/4?
It's like 75%.
75% on a test. Have you ever held 3/4 in your hand? How much money do you have? 75 cents. So there's lots of ways that quarters come into our mind for doing mental math. Does anyone have thirds memorized? Anybody know what 4/3 is? 1.3 repeated. 1/3 is 0.3 repeated. 4/3 is like 1 1/3. Okay, so now what I'm going to do here is I'm going to take out my calculator and I'm going to try to get 0.75. You're going to help me. I want 0.75. What should I start with?
35.
35. Well, 35 is not bad because we did that one already. That's 70%. We're so close. Think we should try higher than 35 or lower? Sam, what do you want to go with? Higher or lower?
Higher.
Higher? How much higher?
Uh,
36 or 40 or how?
30s, yeah.
37? Pretty close. But now we're too big. So we should go a little bit lower. How much lower? 36? Do you want to go to decimals already? What do you think, Zaya? 36 point, give me a number.
2.
36.2. You think she went too low or too, see? Or does she need to go lower? It's like Price is Right. You ever watch that game show? Oh, too low. So now we go 10 of 36.8. We could go even higher, 36.0. I have to hit 10 here. 10. 36.9. Oh, that's really close. Again, we're taking too long, but we could keep guessing and checking. It's kind of fun, right? You kind of like me wasting time sometimes in math, right? Yeah, there's smiles. Oh, we're getting it. It's addictive a little bit too, right? I'm really happy with that. That's like correct to 5 decimal places right now. 36.87. So I'm going to take this triangle and I'm going to draw that I'm pretty excited about 36.87. Now we're going to guess and check for angle F, but we're going to start off with a really good guess. What would be your first guess to 2 decimal places if you had to for angle F?
50.
Oh, I think we could guess better than that. 2 decimal places. First guess. 50 is not bad, but I think we could get closer. Go to calculator. First guess.
52.55.
52.55 is pretty good. I think we could get closer.
How much is it?
Anybody know why I want to guess this number first?
It's 90
53.13.
It's 90 degrees.
Because I have to add up to 90, because the whole triangle has to add up to 180. So that's gonna be my first guess. I'm gonna try it right now. See how close we get to 1.3 repeated if I do tan of 53.13. Ooh, 4 decimals right. Sorry, you know how I warned you I get excited about things that we do on the board? That's pretty exciting. So this idea that tan is opposite over adjacent, and your calculator has them all built in. In fact, we're going to learn later that you can go to this tan inverse button. Probably not supposed to show you this already. We want it to be perfectly exact to a whole bunch of decimals. We got 36.87. It's actually 36.86989765, which takes away some of the excitement of us guessing and checking, because, like I said, the guessing and checking is not bad, but it takes a long time. So whenever there's something that takes a while, mathematicians come up with a way to make it fast. And it's built into your calculator with this little -1 called the tan inverse button, which we'll learn very soon. But right now we're just playing around with tan. Or, there it is, really soon in your notes. It's like the next thing I was going to show you. So we have that tan inverse button to find an angle. And the way that we set things up on our calculator, okay, we're going to find angle K. I'm going to label that in green. And I'm going to write above here, I'm going to remind myself of the definition of tan. Tangent is the opposite side over the adjacent side. So then if I want to write the ratio for K, tan of K, the opposite side is 9. The adjacent, right, because if I go straight across, that's 9. The adjacent side is 13. This, of course, is my hypotenuse, opposite the 90. Kind of weird to have the 90 degrees on the top. And so what we did first is we guessed and checked, right? We said, well, 9 divided by 13, guessing and checking, we need the ratio to equal 0.6923. But our calculator has it built in that the opposite of tan is tan inverse. And I'm going to write it as a step right now, right? In equations, what you do to one side, you do to the other, right? If the opposite was multiplying, you would divide, okay? The opposite of tan is tan inverse. So we do tan inverse of this side, and we do tan inverse of this side. And mathematicians almost never write this step because it's too, I'm telling you, mathematicians don't like writing letters. That's like an essay for a math teacher to write 3 letters. But this tan inverse, since it's the opposite, it simplifies. And what generally happens is we just write this step. So most people in trigonometry go directly from here to here. But I wanted to show you the idea that if you do the tan inverse of both sides, these are opposite. Opposites cancel each other out. You've done that in equations your whole life. Then, but it's a little bit annoying to write that much, so often we just skip to this, and then we go to our calculator, and the tan inverse button is right above the tan button, and now we can go 9 divided by 13, 34.695 to the nearest tenth of a degree, 34.7. And that was way quicker than, right, if we had been guessing, we would have eventually guessed 34.7 and found out that that was better than 34.8 and better than 34.6, right? And you see that the 34.7 is the closest to, but what do we want our ratio to be? 9 divided by 13. We wanted 0.6923, and the 34.7 was the closest of those. All right. We will review this question because we still need to find tan of n on Monday after your quiz. But I hope you're intrigued by trigonometry and how powerful it is already with this first lesson.